Hello, ladies and gentlemen. This is a video worksheet introduction to the Fundamental Theorem of Calculus. We are going to work through a worksheet together. I'm going to ask you from time to time to pause the video to give you a moment to work through a particular problem, and then we'll clarify any questions, or I will draw attention to any important aspects that I feel I need to. The final result will be one of the more useful formulas in calculus, and that is the Fundamental Theorem of Calculus. This video assumes that you are familiar with some of the basics of calculus. For starters, the derivative of f of x is written f prime x, and in terms of position and velocity, the derivative of the position function s of t is v of t, velocity. This video also assumes that you are familiar with the basics of antiderivatives. If the derivative of f of x is f prime of x, then the antiderivative of f prime of x is f of x plus some constant c. If you are okay with these basics, then we are ready to dig into the fundamental theorem of calculus. The problems from this worksheet all ask about the change of a particular function, either a change in position or a change in velocity. This is also commonly known as displacement. For these two problems, you are given a position function called s of t. And number one, you are to find the change in position of s, which you might also call delta s, from t equals 1 to t equals 4. Please pause the video now and take a moment to come up with an answer. To find the change in position from 1 to 4, it's necessary to define the position at 1 and the position at 4. This is done fairly routinely by plugging in 1 into the function. You end up with 1/2. And the position at 4 should be 5. The change then is s of 4 minus s of 1, which in this case is 4.5. Next up, try number 2. This time you are to find the change in velocity of this moving object. Keep in mind though, you are only provided with the position function. Please press pause now and try number 2. If we had the velocity function v of t, this problem would be very straightforward. It would simply be v of 4 minus v of 1. The same strategy we used before when we needed to find the change in position. Luckily for us, though, we are smart enough to recognize that the velocity of the function is simply the derivative of the position function, which we are given. v of 4 minus v of 1, therefore, means the same thing as s prime of 4 minus s prime of 1. Using the power rule, we can find that this function's general formula is t minus 1. Plugging in 4 and 1 gives us the results 3 and 0. The final answer then for the change in velocity is 3. Since we're talking about position and velocity and not just general functions called f or g of x, it's important that we include units in this. The change in position, I'm going to use meters, and for velocity, I'll use meters per second. Next up, please find the change in velocity from t equals 1 to t equals 4, this time given a velocity function v of t equals t minus 1. Please pause now and come up with an answer. In order to give the change in velocity from 1 to 4, which we might call delta v, it will be useful to know the velocity at t equals 4 and simply subtract the velocity at t equals 1. This function should look familiar. It is the derivative of s from the previous problem, so we should get the same answer, 3 minus 0, or 3 meters per second. At this time, please consider number 2, which asks for the change in position from t equals 1 to t equals 4, given this time the velocity function. Press pause now. If we knew the position function s, this problem would be a piece of cake. The change in position, delta s, is simply equal to s of 4 minus s of 1. So what is the relationship between v and s? V is the derivative of s, which makes s the antiderivative of v. If we reverse the power rule, we get s of t equals t squared over 2, also known as 1/2 t squared, minus t and plus c. In the previous problem, that constant c was equal to 1, but we have no such guarantee for this problem. In the end, the unknown variable c doesn't make any difference. We still end up with 4 plus c, that's the result after plugging 4 into s, minus negative 1/2 plus c. That's the result at t equals 1. The c's cancel out, and we're left with 4.5 meters. Now we are going to start generalizing this process in order to get closer to the fundamental theorem of calculus. This time, I'd like you to define the change in position of a moving object from t equals a to t equals b. There is no formula for the position of the object. Simply, we're going to call it s of t. What I'd like you to do is define the change in position with respect to s of t, or in terms of s. Please pause for a moment now and give an answer. No tricks on this one. The change in position is simply s of b minus s of a. Now go ahead and try number 2. Express the change in velocity as best you can in terms of s from a to b. It's pause time. In terms of s, we can express this with a derivative. The change in velocity is s prime of b minus s prime of a, with the understanding that s prime of t is the velocity function. This time, please express the change in velocity from a to b in terms of v. Hopefully you're getting the hang of this by now. The change in velocity given a velocity function is simply going to be v of b minus v of a. Now, last but certainly not least, and the crux of this lesson, please try and express the change in position from a to b, but try to do so in terms of v. On your marks, get set, go! What we really want in order to express the change in position from a to b is a position function. That would be ideal. If we had a position function, we would simply say that the change in position is s of b minus s of a. But how do we express this idea in terms of v instead? We know that the derivative of s is v. The derivative of s is v. But we don't want the derivative of s. We just want regular old s. And we know that s is the antiderivative of v. You might be tempted to say that the change in position, S of B minus S of A, means the same thing as maybe big V of B minus big V of A, where big V represents the antiderivative of V. This isn't a bad way to do it, but this isn't the notation that we are going to use. Instead, we're going to say that this idea is represented by what's called an integral. Integration. Integrate the function V from A to B and do this with respect to t. This squiggly is how we will represent antiderivative, and in particular how we will describe the change of a function, the displacement of a function. Incidentally, this is the fundamental theorem of calculus. It is a way of describing antiderivatives and a way of describing the displacement of a function over an interval. In more general terms, given some function f of x, the change or displacement of f of x over some interval a to b is defined as f of b minus f of a, which is the integral from a to b of f prime of x dx. Another common way of expressing the same thing is to say that the change in big F of x is equal to big F of b minus big F of a, which can be thought of in terms of antiderivatives as the integral from a to b of little f of x dx, with the understanding that f of x, little f of x, plus some constant c is the antiderivative of big F of x, or conversely, the derivative of big F of x is little f of x. So, congratulations! You have learned, you have discovered the fundamental theorem of calculus. So let's finish things off by trying a couple more problems that utilize this wonderful formula. The fundamental theorem of calculus has been included at the top of this page to help you through this problem. You are to find how far a moving object moves, the displacement, from t equals 4 to t equals 7. You are given a velocity function, v of t. In other words, at t equals 4, this moving object has a position. At t equals 7, it has a new position. We want to know what was the total distance traveled during that time, or how far away from that starting position did it end up when it was at t equals 7. Take a moment and give it a shot, and we will compare answers. If we had the position function, this would be a piece of cake. It would just be s of 4 minus s of 1. Instead, we have a velocity function. So this process will involve anti-differentiation of some sort. More specifically, we are going to integrate the velocity function, v of t. We're going to integrate with respect to t, and we're going to integrate over the interval 1 to 4. This process requires the antiderivative of v of t, 2t minus 7. So what we're really doing, more specifically, is we are integrating 2t plus 7 with respect to t. This antiderivative is fairly straightforward. S of t, using the reverse chain, or not the reverse power rule, gives us t squared plus 7t plus some constant c. This formula gives us a position at t equals 4. That's going to be 44 plus c. in a position at t equals 1, which is 8 plus c. Our final result then will be the result of 44 plus c minus 8 plus c. The c's cancel out. We're left with 44 minus 8, or 36, we'll say, meters. That is the total displacement from t equals 1 to t equals 4. Let's try another. Here is the final practice problem. Go ahead and give it a shot. There are a couple different ways to think about this one. One way might be to think about what the total displacement is of this function, which we might call s, and add that to s of 1, which is 10. To find the total displacement, we require the antiderivative. So s of t, chain rule in reverse, t squared over 2 plus 3t plus c. Using this method, s of 4 is equal to 20 plus c, and s of 1 is equal to 3.5 plus c. The total displacement then of s of 4 minus s of 1 is 20 plus c minus 3.5 plus c. The c's cancel out, and we're left with 16.5. This represents the total displacement of the moving object. If the starting position of 1 is 10, then our final answer is going to be s of 1 plus 16.5, or 26.5 meters. A second option for this problem uses the antiderivative function s of t a little more directly. We know that s of 1 is equal to 10. We also know that s of 1 is equal to 3.5 plus c. Therefore, we can solve for c. 10 is equal to 3.5 plus c, and the constant c gets assigned a value of 6.5. If we know the value of c, we can find s of 4 more directly. S of 4 is 20 plus c, which, when c equals 6.5, is 26.5 meters. Well, that's all for now. Thank you for your time and effort, and I hope you've enjoyed learning about the wonderful fundamental theorem of calculus.